My name is Dr. Ken Gallardi, and today I want to build on the features of the complete photon model as developed in an earlier video and show that the photon does not possess a conserved linear momentum. I appreciate that this is a marked departure from current thinking, so allow me to make 4 arguments in favor of my model. Historically, the experiment which has been pivotal in asserting radiation consists of photons and has a conserved linear momentum is the Compton effect. So let me address that issue first. In that experiment, which is schematically shown, one assumes the appropriateness of the relativistic expression for the total energy of a massless photon and uses it to identify the magnitude of the momentum. Then one adds the observed direction of the photon to create the linear momentum vector. In addition, in this experiment, one assumes the interaction is essentially a two-body collision between the photon and an electron, where the electron is both loosely bound and has minimal initial momentum. The setup and output, which is about to be shown, were copied from the reference shown on the screen. Experimentally, one observes that the output spectrum at all angles, measured from the orientation of the input photon, is similar to that shown here for theta equal to 45 degrees. The shorter wavelength peak corresponds to the same wavelength as the incident photon, and it occurs at all angles of the output radiation, although with decreasing intensity as the angle increases. The difference in wavelength between the first peak and the second is what the Compton equation deals with. The accuracy of that equation has been used to validate both assumptions that the radiation consists of photons, each of which obeys this relativistic expression for the total energy, and each one possesses a conserved linear momentum. Now, the momentum vector diagram for the photon at the long wavelength peak is shown, and the difference between the initial and final photon momentum is identified as the momentum of the electron, which is sufficient to send the electron off at relativistic speeds. The challenge to that interpretation focuses upon the output radiation of the shorter wavelength peak, also emitted at 45 degrees. But its wavelength is the same as the incident photons. Before constructing the momentum vector diagram for this output, I want to make 2 points. 1, the wavelength of these incident and output photons are the same, and therefore they have the same energy, which in turn means that no energy was transferred to the electron in these collisions. And 2, if the electron received no additional energy, then it cannot have any additional momentum. Since the initial momentum was assumed to be effectively 0, the final momentum of the electron also is effectively 0. Now I can construct the momentum vector diagram for the output photon. I apply the same reasoning as with the Compton explanation to identify the contradiction. Please note that while I show the analysis for 45 degrees, the results would be identical or analogous for all angles. Constructing the analogous vector diagram for the photon at the shorter wavelength peak, you will notice that the momentum vector for the input photon is the same as above. But now the vector for the output photon is the same length as the input photon vector because they're the same wavelength. But now the electron's momentum is 0, which means that for this photon interaction there is no conserving linear momentum. One would have the same results for other wavelengths, but the clarity when the electron has no final momentum makes this case crystal clear. I suggest that the Compton effect does not provide the claimed proof that the photon has a conserved linear momentum. In another video, I will present this model's explanation of the Compton effect. The second argument I present is with respect to linear momentum, and it relates to the experimental outcome of 2 different experiments. First, the interaction as seen in the double slit experiment, and second, as seen in the 2 possible outcomes when one has double refraction. Let me go through them one by one. First, with respect to the double slit experiment. I've shown in an earlier video on the double slit, when done on 1 photon at a time, that the photons arrive at the screen in the Fraunhofer region in an unpredictable pattern. This unpredictable point of arrival continues for all the photons in the experiment. Now, while one cannot predict the arrival location of a specific photon, the number that arrives at the given point maps out the familiar double-slit experiment pattern. I suggest that the precision required by conservation of momentum is inconsistent with the experimental observation of an unpredictable point of arrival. The second experiment deals with the case where an incident photon is traveling along the optic axis of a birefringent medium, as shown. Upon arrival at the birefringent media, each photon is polarized linearly to match the polarization of either an ordinary or the extraordinary ray. The selection of which polarization is done is purely probabilistic, as was shown in the previous video on polarization. And then the photon travels in a direction consistent with that polarization. This means that the initial momentum is not conserved by the interaction. To emphasize the mismatch, there are two possible outcome directions, or momentums, that a single photon may travel along, corresponding to the polarization of the ordinary or the extraordinary ray, even though it started with a single but different momentum. I suggest this means that linear momentum is not conserved in the example of double refraction. The last argument, and a theoretical one, comes from the features of this complete model. It was shown in the video outlining the model of the photon that quantization implies a causal uncertainty, which in turn implies a probability-based mechanics. This means that one cannot get inside the photon to observe the details of the interaction, and therefore one cannot apply the conservation momentum constraints. This, together with the observed lack of conservation momentum, supports the perspective that the photon does not have a conserved linear momentum. The combined results then is that the Compton effect, when applied to the output radiation at the same wavelength as the input radiation, denies a conserved linear momentum. The double-slit experiment, when you look at the location where the photons arrive, denies a conserved linear momentum. The two directions of an output photon can go in a double refraction experiment, both different than the direction of the incident photon, denies a conserved linear momentum. And the probability mechanics inherent in a complete model of the photon denies the ability to apply linear momentum as a property of the photon. I suggest the consistency between the experimental data and the features of the model should be seen as adding to the credibility of this complete photon model. Now let's look at angular momentum, or spin. Experimentally, it's fixed, and it's either denoted +1 or -1, and it can't be changed. Sometimes the spin has been correlated to the polarization, but the photon can have three distinct polarizations, left and right, circular as well as linear polarization, and furthermore, these polarizations can be freely changed. It is a suggestion of this model that the spin is not correlated with the polarization, that is, the rotation of the direction of the fields, but rather to the rotation of the magnitude of the fields. A rotating magnitude rather than direction may be harder to visualize, but we've come to easily conceive the rotation of the direction independent of the magnitude. But consider a moment the direction fixed and the magnitude rotating. And that picture is just a shift in frame of reference from when the direction is rotating and the magnitude is fixed. The correlation may be more difficult to conceive, but this model suggests that spin is the rotation of the magnitude of the fields. In summary, this complete photon model implies that the photon does not possess a conserved linear direction, momentum, and spin is the result of the rotation of the magnitude of the fields. Well, thanks for watching. I appreciate your comments, and I appreciate it when you pass this channel on to others, particularly those in the physics community. Thanks again for watching. Please subscribe and you'll be notified when I post the next video, which will deal with the nature of the fields and energy, which is perhaps the most fundamental issue in physics. Thanks for watching, and God bless.